Okay, let's talk about the random variables. So random variables are mappings from events to real numbers or integers. And if a random variable x takes countably many or finite number of distinct values, and then this is a discrete random variable and it will have a probability mass function. Okay, so if it takes infinitely many number of possible values, then it's a continuous random variable, and we will talk about the probability distribution function. So as a convention, note that random variables will be denoted by capital letters, and the specific values of random variables will be denoted by the small letters. So as you might already know, the discrete random variables are taking a finite number of possible values, and each possible outcome is coming from this set of outcomes, which is denoted by this capital S. And you can see the probability that this random variable x takes the value xi is denoted by small p, and by being a probability measure, or definition of being a probability requires this condition that the sum of all the probabilities should be equal to 1. And we have this cumulative distribution function denoted by capital F, and you can see what we have here, which is given by the cumulative sum. So probably the most common continuous random variable we will talk about in this course will be the normally distributed random variables. And you can see here we have the probability distribution function, the so-called PDF of this normal random variable is given here. And you can see the notation: x is normal distributed with mean mu, and the variance equals to sigma square. The domain of our x is on the real line from minus infinity to infinity, and obviously by being a probability distribution function, we must also satisfy the condition that if we integrate this over the domain of this random variable x, we should get equal to 1, just like the probability mass function. And the expected value of the normal random variable is e to the x, expectation of x equals to mu, the variance equals to sigma square. In general, if you want to calculate the expected value of a continuous random variable, then what you will do is actually, like for the normal distribution, you will multiply this with x and integrate. So that's going to be the expected value of x. And similarly, you can calculate another useful quantity here for the second central moment of the random variable x. And you can remember that we have the variance formula. The variance of this random variable can be calculated as follows. So this can be used to calculate the variance of the random variable x here. So for the normal distribution, which is, as I said, is going to be commonly used in our course, and especially also for hypothesis testing, normal distribution is very important. So you can see that it has a single peak. It is the so-called bell-shaped curve. And if you take this interval with one standard deviation plus or minus from the mean, the area under the curve that corresponds to this area, this covers basically about 68% of the total area. And if you take a bit larger interval, which is plus or minus 2 standard deviation away from the mean, then you can see that we might get around 95% of the total area. Later on, we will also talk about, or we will also use some properties of the log-normal random variables. A log-normal random variable is obtained when you take the exponential, if you basically have a normal random variable x, and if you exponentiate that random variable x, then what you get is a log-normal random variable. And especially when we modeled asset prices, the stock prices, we will talk more about the log-normal random variables. And here we have these three properties of the log-normal random variables, which are going to be quite useful later on. So we are not going to derive these properties. For the derivations, you can refer to some statistics textbooks. However, we will be using these properties later on. I would like to briefly go over a few more useful properties that we might use. So the variance-covariance, we know what's the meaning of covariance from statistics, introduction to statistics. And basically, if you have the covariance of x and x, that's the same thing as the variance of x. The second property here tells us that covariance of x and y is the same thing as covariance of y and x. So this covariance operation is basically symmetric. In the third property here, you can see that we have a scalar here. So this is not a random quantity. So if we have a multiplication of a times x, so this x is a random variable and a is a scalar, so we can take this scalar out of the covariance. So this is just the same as in the expectation operator, because a is not a random quantity, so we can take it out of the expectation, and we can also take it out of the covariance operator. This fourth property here tells us that the covariance of random variable x and another random variable y plus z can be decomposed as covariance of x and y plus the covariance of x and z. So this tells us the covariance is a linear operator, and we can decompose these terms one by one. And the fifth property here is about the variance of a sum of random variables xi. So when we have, let's say, let's do a small example here. If we are talking about, let's say, the variance of x1 plus x2, so what we are saying is you will sum first the variance of each of these individual random variables. So that will give us the variance of x1 plus the variance of x2. And then in our simple case, the cross terms, we only have one cross term. That's going to be the covariance of x1 and x2. You can repeat this example for 3 random variables, right? So you are going to get the variance of x1, x2, x3, and then you will have the cross terms. x1, x2, covariance of x2 and x3 plus 2 times covariance of x1 and x3. Okay. And finally, the last property is about the correlation coefficient. We denote this by rho. So this gives us the correlation between two random variables x and y, and it can be calculated using this formula. The conditional expectation, here in this example, the first part we have for the discrete random variables, and the second case is for the continuous random variables. And for the continuous case. So both cases, they are quite similar to each other, and how you can calculate the conditional expectation of x given another random variable y is equal to some particular or specific value y of j. Okay, so this can be calculated by the sum of all these possible xi values by multiplying with the conditional probability of x equals to these xi values and given this condition or conditional event y equals to yj. And also remember from statistics that the same equality we can rewrite the conditional probability in terms of the joint probability divided by the marginal probability of y being equal to yj. And similarly for the continuous case, for the continuous random variables, the conditional expectation of x given this y can be written using the conditional distribution of x given y. Now we have a continuous distribution, so we have to take the integral of this distribution. But still, you can apply a similar property here. So the conditional distribution can be calculated from the joint distribution of x and y divided by the marginal distribution of y. So this is the marginal distribution, and here we have the joint distribution. There are a few more other useful properties of the conditional expectation. Again, we are not gonna derive these, or we are not going to prove any of these properties, but I would like you to keep in mind or refer back to these properties later on when we talk about some stochastic models or modeling the asset prices. Some of these properties will be useful for us.